Here we have a theorem based on the composition of linear map, which is given. See, let T1 and T2 be two linear maps from U to V, and S1 and S2 be another two linear map from V to W, and they have given P is another linear map which is from W to Z, where UV, W and Z are vector space over the same field of scalars. Then they are asking to prove this 5 point. So we'll prove one by one every point. So start with first point. Before starting first, we will write what is mapping T1, T2, T3 and S1, S2 and P, how they are defining. So T1 is the mapping from U to V, T2 is a mapping from V to W, S1 is a mapping from V to W, S2 is a mapping from V to W, and P is a mapping from W to Z. From these five mapping, what we can conclude? First of all, see, we can map two mapping only if they have same domain and codomain. So from this we can see that I can add up T1 and T2, S1 and S2. But if they are asking to add me S1 and T1, so it is not possible because both have different domain and codomain. So from this we can say that T1 plus T2 is defined, S1 plus S2 is defined. And also, no, these two mapping are only defined. And what about the composition? I can say T1 S1 S1 T1 composition is defined. That means composition of these two mapping is defined, composition of these two mapping is defined, composition of S1 and P is defined, composition of S2 and P is defined. These are the thing which initially given in the question which we can think about. So from first one they are asking S1 plus T1 plus T2 is equal to S1 T1 plus S1 T2. So before starting this, first of all we have to see that is T1 plus T2 is defined. So yes, we have already seen that T1 plus T2 is defined. Again there is a question, product of S1 T1 plus T2 is defined. That means they are asking whether the composition of these two is defined. So yes, because T1 and T2 are mapping from U to V, so their sum is also from U to V. So U to V and S is a sum mapping from V to W, so obviously it is defined. So we'll write first, since T1 and T2 are linear map from U to V, therefore we can write T1 plus T2 is a mapping from U to V, and also S1 is a mapping from S1 is a mapping from V to W. So one is from U to V and another one is V to W. From this we can say that the product of S1 T1 plus T2, S1 T1 and S1 T2 is defined and are from U to W. So we can write S1 T1 plus T2 is a mapping from U to W. S1 T1 is a mapping from U to W, and S1 T2 is a mapping from U to W. Now we'll prove the first part of the theorem. So we have to always write all these things before proving any part of the theorem, because if we know that this thing is defined, then only we can prove that. So let us start its proof. So we have, for any scale, for any vector u belongs to U, we can write S1 T1 plus T2 of U is equal to, see, this is the composition of two map. So I can write this as, using the definition of composition, S1 of T1 plus T2 of U. I can write this from the definition of composition or we can say product. Now, since T1 and T2 are linear, so I can write this as T1 of U plus T2 of U. I can write this by the definition of addition of two linear map. Definition of addition. LUV. Again, S is a linear, therefore I can write S1 T1 of U plus S1 T2 of U. Every time you have to mention reason since S is linear. Again, from this I can write S1 T1 of U, S1 T2 of U. Again, I can write this by the definition of product. Definition of product, or you can write composition. Both are same. You can use whatever you want to write. If you will write definition of composition, then it is also correct, and if you write definition of product, then also it's correct. So from this we can write S1 T1 plus S1 T2 of U. So we have started with S1 T1 plus T2 of U, and we are here with S1 T1 plus S1 T2 of U. That means I can write S1 into T1 plus T2 is equal to S1 T1 plus S1 T2. So here we have proved our first part for all U belongs to U. Now for second one, again first we'll write what we have to prove. S1 plus S2 into T1 is equal to S1 T1 plus S2 T1. See here you can pronounce it as S1 plus S2 of T1, like a composition. S1 plus S2 of composition of T1, and S1 composition T1, S2 composition T2. Also you can read as product of S1 plus S2 T1 and product of S1 T1 and product of S2 T1. So we'll prove is, before that, is S1 plus S2 is defined, or is product of S1 plus S2 T1 defined? Is this defined or is this defined? So we'll see. Since S1 and S2 are mapping from V to W, S1 is a mapping from V to W and S2 is also mapping from V to W. This implies that the addition of S1 and S2 is defined, and this is mapping from V to W. Also, S1 is a mapping from V to W and T1 is a mapping from U to V. So I can say that S1 T1 is defined, which is from U to W. Again, S2 is a mapping from V to W and T1 is a mapping from U to V. That means that S2 T1 is defined, which is from U to W. So we can conclude that S1 plus S2, S1 T1, product of S2 T1 is defined. So we'll start its proof. Now for any U belongs to U, we'll start with S1 plus S2 of T1 of U. That is product of S1 plus S2 T1 of U is equal to, we have to prove that. So we'll start with S1 plus S2 T1 of U. This I can write using the definition of product. Again, since S1 plus S2 is a linear, so definition of addition in LUV. Using this we can write S1 T1 of U plus S2 T1 of U. From this I can write S1 T1 U plus S2 T1 of U by the definition of product. Again, from this I can write S1 T1 plus S2 T1 of U. If both these are equal, then I can write S1 plus S2 T1 is equal to S1 T1 plus S2 T1. So hence we have proved second one also. Now we'll prove part C. In this they have asked to prove that P of product of P S1 T1 is equal to product of PS1 T1. So we have to prove this. Before that we have to check whether these type of composition is defined or not. So first we will check it is defined or not. So suppose they have given that S1 is a mapping from V to W. P is a mapping from W to Z and T1 is a mapping from U to V. These three mapping is already given and they are asking for these three. So first of all, S1 T1 is defined or not? We already know that S1 product of S1 T1 is defined and which is from U to W. Now product of S1 T1 is from U to W and they are asking with product with P. So this is from U to W and this is from W to Z. So obviously we can say that from here also we can say that the product of S1 T1 is defined and which is from U to Z. Again we have to see this one. So first of all we will check the product of PS1 is defined or not. Here P is a mapping from W to Z and S is a mapping from V to W. So V to W and W to Z, that means this mapping is defined. So we can say that P of S1 is defined and this is defined from V to Z. Okay, and now product of PS1 T1. So PS1 T1. So PS1 is defined from V to Z and T1 is defined from U to V. That means U to V, V to Z. That means this mapping is also defined and this is defined from U to Z. So it is very clear from these mapping that these both are equal and we have to prove it just theoretically. So let P of S1 T1 of some element, let it be U, for any U belongs to, this U belongs to capital U, so for any U belongs to U. Now from this I can write P of S1 T1 of U by the definition of composition, definition of product. Now from here P of S1 T1 of U, I can write this again by the definition of product. From here I can write P of S1 and T1 of U. Again I can write this by the definition of product. From here I can write P S1 T1 of U. So from here we have concluded that P of S1 T1 is equal to P S1 T1. Here we have proved third part also. Now we're left with fourth and fifth. D, we have to prove that alpha S1 T1 is equal to alpha S1 T1 is equal to S1 product of alpha T1, where alpha is scalar. So we have to prove this thing. To prove this, again we have to know whether the product is defined or not. So first of all, see, we have S1 is a mapping from V to W. Therefore, alpha S1 is also mapping from V to W. These things we can remember easily because we have already studied that the sum of two linear map is again linear, composition of linear map is again linear, and if we multiply any scalar by the linear map, that is also linear. So from that we can write this: if S1 is a mapping from V to W, then alpha S1 is also mapping from V to W, and which is linear also. Now for the second one, T1 is the mapping from U to V. Therefore, alpha T1 is also mapping from U to V. And we have already S1 and T1, product of S1 and T1, that is the composition of S1 T1 is a mapping from V to W. And also, now we have to see about this one. See, alpha S1 is the mapping from V to W and T1 is the mapping from U to V. So, alpha S1 T1, product of alpha S1 T1, that means U to V, V to W is also defined, so we can write alpha S1 T1 is a mapping from U to W. And for this, product of S1 and T1 is V to W, and if we multiply alpha by this, then we'll get alpha S1 T1 is a mapping from V to W. Also, product of S1 alpha T1, alpha T1 is a mapping from U to V and S is mapping from V to W. So this is mapping from U to W. Now let us start its proof. For any U belongs to U, alpha S1 T1 of U is equal to, so we have taken one side, alpha S1 T1 of U is equal to, using definition of composition we can write alpha S1 T1 of U. Again we can write this as alpha S1 T1 of U, since this is linear mapping, so we can write alpha outside. Again we can write this as S1 T1 of U can be written as S1 T1 of U because it is a composition. Again here we can write alpha S1 T1 U. This implies that we have find out what is the value of alpha S1 T1, which is nothing but alpha product of S1 T1. We can calculate this, then we can write similarly alpha S1 T1 is equal to alpha S1 alpha T1. So we have done our fourth part. Now for fifth one, let E is equal to, it is given that IV T1 is equal to T1 and T1 IU is equal to T1. So we have to prove this. So here only we will understand what is the meaning of IV, and if we multiply, that means if we are taking product of IV and T1, then we will get T1, sorry. So first of all, what is IV? So we can understand, or I think you know already that, okay, I am writing this over here. Suppose I have any mapping I, and this is mapping from U to U. I will call it identity mapping. This is if it is defined like I of U is equal to U, then I will call it identity mapping, or I will denote this as IU. So now you understand what is meaning of IV. IV is nothing but identity mapping from V to V, and IU is nothing but the identity mapping from U to U. So let us continue our question. So we have to check whether this is defined or not. So first of all, IV is nothing but mapping from V to V. IU is nothing but mapping from U to U, and we have already T1 is a mapping from U to V. So first one is, so from composition of IV T1, that means T1 is from U to V and IV is from V to V. That means this composition is defined. So yes, composition of IV T1 is from U to V. Similarly, T1 IU is a mapping from U to U, and T1 is a mapping from U to V. So this is also defined. Therefore, T1 IU is mapping from U to V. So both mapping are defined. So we can continue our question. For first one, for any U belongs to U, IV T1 of U is equal to, using the definition of composition, we can write IV T1 of U. This is equal to, this is nothing but, if T1 of U is nothing but, see, for this you can see thing like, if here it is U, then T1 U will be here, and this is U and this is V. Okay, we need to delete this. Okay, for the solution, for first part, we are taking for any U belongs to U, IV T1 of U is equal to, using the definition of composition, we can write this. So for this, we will see this. See, if we are considering any element, U belongs to this first vector space U, and through this T mapping, it will map over here in the V T1U, which is nothing but V, and we are giving IV. IV means this is somewhere map here V to V. See, you can understand by this, it is not given identity mapping, but you have to understand there is another mapping which is IV from V to V. So if I am considering one element from this and I am taking here, then it will remain same since it is identity mapping. So through this, IV of T1 of U is nothing but T1 of U only. So this will be T1U, because all T1U belongs to V. Therefore, product of IV T1 is nothing but T1. Similarly, for any U belongs to U, T1 I U of U is equal to T1 IU of U. Again we can see this also by mapping. See, u to u, this is iu, and u to v, this is t1. So if we are taking any element here, and through this through this iu mapping, it will map iu of u here. So, but this is identity mapping, so obviously it will be u only. So from this I can write t1 of u. If this is equal, then I can write t1 of iu is nothing but t1 only. So we have proved our last part. So it is clear that composition of t1 iu is nothing but t1, and composition of iv t1 is nothing but t1. So here we have done this theorem. We'll do next theorem.